Am I audible now?
Hello, Vikas. Am I audible? Hello. Vikas, are you able to hear me? Are you there, Vikas?
Okay, guys. I think we can start now. It's been already 10 minutes late. So just give me 2 minutes.
Vikas, you are not audible. I'm so sorry, everyone. Looks like Vikas is having some technical issue. Just allow me a couple of minutes while I get the issue resolved. Hi everyone, looks like there was some technical issue from our speaker's end. We are trying to get it resolved. Please bear with us for a couple of minutes. We will be starting soon. Hi Vikas, is it better now? Are you able to hear my voice?
Yes, you're audible now. Yeah.
Okay, perfect. We will be starting soon.
Okay.
Soon. Give me a couple of minutes.
Yeah, sure. Okay.
Okay, so before we kick things off and I hand it over to our speaker, a quick recap of the housekeeping items. We are recording the session and the session recording will be available on our YouTube channel. The link you can find in the chat section. Also, please use the Q&A section to ask any questions you might have during the session, and we will do our best to answer them as the data progresses towards the end. Also, we will be sharing a feedback poll towards the end, and all of you are requested to kindly fill that up. And e-certificates will be provided within 24 to 48 hours of the session, and it will be provided only to those who have attended the entire webinar. So please stay tuned with us till the end. And now on to our speaker. In this session of data, we have K. Vikas with us. Vikas is an NIT Rourkela alumni and a staff data scientist at Avlino who has made significant contributions to the field of machine learning and operations research. With a background in mathematics, Vikas has spent the last 5 years exploring various aspects of machine learning, including classical ML, deep learning, and big data. So before I hand it over to our speaker, here is a quick announcement that we are making this session live on YouTube and it will be streamed there. So over to you, Vikas. You there?
Yes, yes. Thank you. I said thank you for the introduction.
You're welcome.
Yep. So, hello, guys.
Vikas, it looks like the glitch is still there. As soon as you started sharing, you went on mute. I'm not sure why is it happening.
Sharing, then just a minute. I will just share the entire
You
screen.
are audible now. I can hear you, but
Yeah,
last.
maybe it's because for some sharing issues. Am I audible now?
Yes, yes, you are audible now.
Okay, it's maybe the Chrome issue, something. I cannot share one single tab, something like that. Okay.
It's better now. It's perfect.
It's
You can
perfect,
start.
right? So, yeah.
Yeah.
Just I'm continuing. So today's topic is basically we'll be discussing ensemble methods. So a quick table of contents, like what we are going to do. That is basically we will understand what ensemble methods are and what are the types, and we'll go in detail how the flow works for different types of methods and what are the conclusions. We will learn different algorithms for different mechanisms, that is methods. And in short, we'll be using some Python packages. So already Asid has given an introduction about me. So my name is Vikas. I'm working as a staff data scientist at a startup called Avlino. So I have 5 years experience, and areas of expertise are classical ML, deep learning, which is confined to computer vision and NLP. And right now I'm working on operations research. So yep, I like to travel, playing FIFA, and so before we start, what I expect from you guys is basic understanding of machine learning, especially supervised machine learning and ranking, Python, and a little bit of enthusiasm. So I won't be focusing much on mathematics. That is, we won't be going deep into mathematics because covering mathematics itself takes a lot of time. So I won't be able to complete the entire ensemble methods in this session. So I'll be giving a little bit of mathematics, but we will not deep dive into it. So yeah, before we start, so I think hope everybody is ready. So let's begin. So basically, ensemble methods are nothing. It's a category of machine learning techniques which combines multiple models to improve the overall accuracy and the performance of the predictive models. So basically, when we say that it combines, it takes various types of models, for example, decision trees or neural networks or regression models or any kind of models, and combines them to give an aggregated or improved prediction or accuracy, which we say that. So when we say that combining, so when we define the base models, we call them as weak learners. For example, why it is required? Because in reality, the data which you are problem solving, that is the real time, real life data, is very sparse and there is a lot of bias and variance in it. So when we have heard about, like if you are acquainted with the types of biases, so when we collect the data, that is sample of data from the real life problem statements, we already induce a selection bias in that. And coming to inductive bias, after doing the selection bias, when you do future engineering and future selection on it, you already introduce another bias. So the bias keeps on increasing. So to reduce that, what we define is that we define multiple models, which are called weak learners or base learners, and we combine them to get to a supervised or strong learner, or we can say that improved accuracy. So that's what it is. There are certain models which do well in one aspect of data are called multiple models of base learners, and we combine them to give a final model which is called a strong learner. So the main thing is basically to get rid of the biases and the variances. Uh, this is the first most objective in it. Now, coming to working of ensemble methods, there are two types of mechanisms. One is parallel mechanism and one is sequential mechanism. So parallel mechanism is nothing but the base learners which we trained are, or base learners which we trained are trained in parallel. That is, each and every data which we are taking have been sampled out separately and we train the model separately, and we train suppose 5 weak learners or 5 parallel models and then we combine it. Whereas in sequential methods, what we do is basically we train one model, we get the output and we fetch it, and we give input to another model, and then we train it from there. It's basically improving the error, or reducing the error or increasing the accuracy by doing the sequential learning. The main motivation behind parallel learning is basically dependency of each base learner. That is, each weak learner or each model contributes equally in parallel learning. Whereas in sequential learning, it's the connection between them. That is how the error is migrating or how the accuracy is improving from one learner to another learner. So the example of parallel learning is basically random forest, whereas the example for sequential learning is called, we can take it as adaptive learning. So I hope there are no doubts till now, the mechanisms till now. If there are any, so kindly please. Uh, so okay, we will take that in a question and answer, right? Or else we can do right away.
You can, Vikas. If you want to take it right now, you can take it.
Okay, okay. So I think hope is there any questions till now, or we can proceed further? I'm getting okay. Someone has raised hand. Okay.
Okay, so
Uh,
Chirag is asking, won't combining them lead to more required sources and computation time?
Okay, it depends upon different problem statements. So what your optimization. So the one is optimizing your resources or optimizing your accuracy or optimizing your final output. So it depends upon what's your objective is. If you're understanding from business perspective, if your business is well established, if it's an MNC, you won't be focusing on resources, right? The computational power comes when, like for example, if you're training a lot of ensemble methods together, you need a lot of computational powers. You need expandable computer engines like EC2 engines, which are in cloud, like maybe AWS, Azure, or GCP. You can use those, which is again not a restriction for you. Now, coming to time, again, there is a restriction here. Yes, if you are time constrained, but you have to trade off between the time. For example, if you're training 2 to 3 days and you're getting, say, 90% accuracy or 85% accuracy, which is again a huge thing, and but if you're training for 5 hours and you are getting 70% accuracy, then obviously you will be going for the 5 hours training. So it depends from objective to objective. And now combining the methods will again follow this path what your objective is. So did I answer your question, Chirag? Yes. Yeah, Swaminathan has yeah.
Yeah, Vikas, thank you. I think thanks for bringing this wonderful session. So I have just two questions in my mind. So when you talk about the parallel ensemble and sequential ensemble, so ideally when you say ensemble, I believe it's sequential operations. So basically for every iteration, you try to improve the weak learners, what you see in the past. By moving in sequential manner, you basically increasing the accuracy or increasing the predictability power, right? So when you talk about parallel ensemble, my question is, does each methods that I'm going to run parallelly will going to see the same quantity of data, or it is like some portion of data? Like what I want to convey is parallel ensemble somewhere related to or similar to random forest? Because in random forest, we just give you the portion of data to different parallel systems. So in the
Mhm.
in parallel ensemble, my question is, are we going to pass all quantity data, all data together in the same model, or are we going to share only portion of the data?
Okay, it depends upon already you have defined. Like for example, if random terrace or in random forest, what we do is we do a bootstrapping. And what bootstrapping means is you select a certain sample of data, not entire data, and in that sample also you leave some certain features. You select, or suppose there are 10 features, you will select 8 features or 9 features, and then you proceed further in parallel in random forest. That's
Yes.
called bootstrapping. Whereas there are certain methods, simple averaging, where you use entire data without sampling entire data. You train different models. For example, you have trained linear regression with L1 regularization, you trained a linear regression with L2 regularization, and now you combine those two. So it's a parallel ensemble methods where you're training entire data samples along with all the features. These are also called ensemble methods. Whereas in parallel methods, there is another thing is called, it's called bootstrapping, where we sample it out and we sample the features also, and we train different models and combine them. There are both the methods are there. It depends upon which one you want to use.
Okay. So now when you talk about like now you just mentioned in parallel ensemble also, sometimes we tend to pass entire data to each model, or sometimes we just sampling the respective data along with features and we pass it. So somehow
Mhm.
it's coming like a bootstrapping only, right? I believe. So in that case, how does that
No, no,
deviated from random forest?
no, 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 no. What do you, when you understand bootstrapping like this. If you have 100 sample of data, you randomly sample of 10 points of data. You have to define the subsample size. Okay. And when you define the subsample size, you add a factor to it. They basically you sample it out of 10 features, you will exclude one feature. So it's basically you are basically telling which feature to exclude. And in random forest it does randomly, you will not be telling, it randomly excludes. But in certain parallel methods you can tell which feature to exclude. But again, When you say that, you are telling that which feature is important for me and which feature, if I'm not discarding, what will be the split, what will be the accuracy. This is called bootstrapping. Whereas when we are considering the entire method, we are not doing any feature selection here. We are putting the entire data, entire features to a particular model on training in certain parameters, and we are switching to another model and we are training completely data. We are not considering any subsample here. So understand me here.
Yeah, that's what my question was. Okay.
So it's totally different from bootstrapping. It's totally different from
Yeah,
random forest. So
yeah.
random forest is subsampling, and
Yes.
subsampling in both size and yes. Okay, you understand it? Yep.
Yeah. I understand. So that's what. So I see. My inherent thought, my inherent guts, right? Okay, these both are different. When you say parallel ensembling, the concept itself is different, and when you talk about bootstrapping in random forest, the concept itself different. I just
No,
want to
no.
confirm.
So parallel, remember the mechanisms I'm saying. So parallel means you have 100 instances, 100 parallel instances running together, and then you are combining. Whereas sequentially, you are training only one model.
Yes.
After that, you're propagating that error or else accuracy to another model. It's one
Yes.
after another. Whereas in parallel, you're going together like say 10 models or 20 models. Whereas in bootstrapping, you're subsampling, but in other models, you're not subsampling, you will be using complete data.
Yeah. Okay. So here, so when you say parallel ensembling, I'm passing entire data set to all 20 models if I'm considering 20 models in
Mhm,
parallel, right?
mhm,
Is my understanding
mhm.
correct?
Okay.
Is my understanding correct, Vikas?
So it depends upon which algorithm. If you're not using bootstrapping, if you're using just parallel messaging, then it's fine. Yeah. So you have to
Yeah.
be clear whether you're doing your bagging and bootstrapping, or you're just simply training parallel 100 parameters and then combining.
Okay.
So,
Okay.
okay, I will come in further slides. It will be more clear to you.
Yeah.
Okay,
Sure,
so
Vikas. Thank you.
yeah. So, are there any other questions? Because someone is returning chat. Okay, does the weekend of para computational must be the same? Can I didn't get your question, whoever has written it. So don't combine the weak learners with the parallel and sequential. Parallel and sequential is a mechanism which is defined for ensemble method, but weak learner is a model. So weak learners can be different, can be same. It depends upon the choice of learners which you're using. These are basically machine learning models like logistic regression or linear regression or anything like that. Whereas parallel and sequential are not models, but they are mechanisms which are incorporated for different models, and we arrive up to a conclusion. So I think whoever asked this question, I hope I have answered this question. Okay, let's move further. So the significance which we achieve by using ensemble methods in real life problem, by solving in real time problems, are basically improved accuracy and reduced overfitting and the robustness and flexibility. And apart from this, I have already said that basically getting rid of biases and variances. So now here comes the thing that is the ensemble methods types. The first comes a simple averaging. So averaging is nothing but again a parallel mechanism in which you train different models using complete data and complete features, which we were talking before, and then you simply average it. For example, I am training a regression model and I have trained three different models, and they have given me say probabilities P1, P2, and P3. I will simply average it by the number of models and I'll be getting the probability of the aggregated one. And whereas in classification, the mode is considered. For example, whatever the classifiers have classes, the, for the test case, I will consider the mode of that. And the other case, what we can do is we can simply consider the argumentative max of the sum probabilities of the each class. For example, it is a binary classes and I am trying three classifiers. I will sum up for the all the probabilities for each class from the three, and I will consider the argumentative max and I will simply classify it. So the limitation is obviously each model have equal contribution. So you cannot tweak down which model is doing better, which model is doing less. So this is simple averaging. And there's in weighted averaging, what we do is we give a weight to a separate model depending upon its accuracy. And the condition is, for example, there are three models. The only condition is the sum of weights for each model should be equals to 1. I hope it's clear till now. Okay. So the second method is bagging or bootstrapping, which we are discussing initially. In bagging and bootstrapping, what we do is we train multiple instances of the same model, but on different subsets of the data. That is basically we subsample from the sample of data by using different techniques. There are different sampling techniques. We can use different sample methods depending upon the problem statement and the use case which you're solving. And we train different instances of the same model. For example, if you're using decision tree, we'll be training multiple decision tree. If you're using basically linear regression, then we'll be training multiple linear regression models. If you're using simple say logistic regression, we'll be training multiple logistic regressions. And then we'll be basically combining these models together to get a final output. So the steps involved are basically generate a random sample from the original data set, which is called bootstrapping. The second thing is basically training the multiple models on different samples of matter. And here again, the training differs from different methods. For example, if I say like in case of logistic or linear regression, we can use L1 and L2 regression, regularization for pruning or whatever, say feature selection of few things. Whereas in decision tree, we can split up the data like number of maximum depth and number of splits so that we can prune the number of trees and number of nodes, and we can further basically merge into final simple data, and then we can combine the entire models to a final model that is a strong learner from the weak learners, and we can get the final outputs. But in random forest, what you can do is you can also get like specified models. For example, if you're trying three trees, you can get each tree model from that output also. N-fold, we basically say that n-folds. N-folds is basically when you are saying 3, the n-fold will be 3, and you'll be having 3 trees together or trained, and then we combine the 3 trees using a loss function. In mostly it will be an aggregated loss function, that is root mean square error or else mean squared error, something like that. In case of classification, it will be log loss, and we'll be getting a final output or final prediction which we want in case of classification or regression. I hope till here there are no doubts, or if there are any doubts, then we can take here. Okay. Okay, someone has asked, how do you decide which of the machine learning analysis to combine together and used as an ensemble algorithm? Okay, well, so you're asking about weak learners, or how many weak learners, which weak learner to pick up or which weak learner to lose. So if you're asking like which weak learner or base learner to pick up, it's entirely up to you. You can use simple decision tree and combine them, or you can use logistic regression, you can combine them, or you can use a mix of logistic regression and decision tree, and then also you can combine them. It depends upon you. But if you're fixed to basically bootstrapping or bagging method, then you have to be careful that you have to use only one kind of base learner. You cannot use a mix of base learners, that is logistic regression as well as decision tree. You have, if you're using bootstrapping method, you simply have to use decision trees, and you have to basically train multiple decision tree and then combine. Or else if you're using logistic regression, you have to use multiple you have to train multiple logistic regression and then basically train. And now coming to like, how does it reduce overfitting? I hope it's done, the first question. And now coming to like, how does it reduce overfitting? So to understand that, simply overfitting is nothing but whatever data you have, you are overfitting. The model is learning to your data set, your sample set, but it's not generalizing to the real data set, because that's what I said initially. Selection bias. Selection bias is nothing, it's one of the types of biases which you incorporate while you are selecting the data. So when you are solving a real life problems, when you come to industry, you are solving the training the model is just 20 to 25% of your problem. The 70 to 70% of problem is your data collection, that is a sample collection, data cleaning, data preparation, feature selection, and feature engineering. These are the things which we do in a real life problem. So when the data is contains that much of noise and that much of variance in it, and you train a model in that, basically the accuracy will be less than 50% or 40%, which you'll be getting in it. But when you use different types of ensemble methods, the thing which you are saying is basically you are creating subsamples of your sample set data, and you're training different samples, not you're showing only one of your data, but you're creating a subsamples from different features also. So the learning is different. It's not only considering the sample set data as future data, but in the sample set data you're calculating more subsamples, and from subsamples you're again sampling the number of features. So each model is learning differently from different types of data points and different features. So in that way, it's generalizing. It's not giving weightage to entire your data population or entire population for in your case, but it's basically overcoming, considering the subsample, it's overcoming the overfitting problem. So I hope it answered your first question.
Yes, Samir, you are correct. Vikas, let's take Q&A at the end of the session because the other attendees are
Okay.
able to grasp the knowledge you were trying to present. So, so everyone, please put your questions in the Q&A section, and we will be taking the questions towards the end of the session.
Okay, sure that. So I hope bagging is clear. So the example which I was discussing right now is basically random forest. It's one of the most popular and commonly used algorithm. And the base learner is basically decision tree. So when you are using bagging algorithm, I have already said that you have to fix the weak learner. You cannot change, or you cannot use multiple different base learners. If you are using decision tree, the entire models, different models should be decision tree. If you're using logistic regression, the entire model should be logistic regression. So in random forest, the base learner or the weak learner is decision tree. So we will be training multiple decision trees and then combine them together to get the output. Now here the catch is the name itself suggests that it's random. So we were talking about the sampling techniques. So in random forest, the sampling is done at a random. So you have to just basically you have to just speed up the computational power. That is, you have to set the random seed, and then it basically calculates the sample size. Say it's 10 you have given out of 100, and it will pick randomly 10 data points. And the feature selection is basically given again randomly. Out of 10, there are say 10 features in your data set. It will randomly select 9 features, and one feature it will be left out. And again, the split, simple decision tree splits. The first split will be based on the entropy. Obviously, I won't be going into further details because it will again take a lot of time for me. But it's the split again takes on base of entropy, or else you can say information gain or information loss. And then we will keep having those things. We can also prune the decision tree, as you all know, and at a random forest level, at a bagging level forest, we can also prune the decisions. We can tell the random forest what will be the maximum depth of it, and we can also tell that what will be the maximum leaf size or maximum leaf nodes in a particular decision tree node. So you can train the random forest in by setting the different kind of parameters in it. Now coming to the decision tree, when I'm saying the subset, the most important thing is that each decision tree should be decorrelated. That means when you're selecting the features out of 10, I'm saying when I'm 9, you are leaving the one feature. So there should be a non-collinear between them. To maintain the non-collinearity, we train a decorrelated trees. That is, there is no correlation between one tree to another tree. So when your feature engineering or feature selection with whatever you are doing it, we are maintaining in that way that there is no correlation between these two trees, and then we are aggregating it. But again, but okay, I will discuss this later. Right now, we have to ensure that, but there is a probability that there is a correlation between two features, and when you're selecting those features, the correlation will exist in certain trees. So it is not entirely done, but the correlation still exists in case of random forest. But in case of other tagging methods or else boosting methods, the correlation will be reduced. So we'll discuss in further. But right now, let's proceed further with random forest. The final prediction will be again simple averaging, what we are saying, or else you can define as a loss function. In case of say averaging, you can define function of mean squared error, or else you can define root mean squared error and then reduce that one and retrain it again and again. And again, it overcomes fitting. Since why it overcomes fitting? Because we are already sampling it from the subsamples. So we are showing the data like a sample size, not the entire data at once, and training it to achieve 100% accuracy. Whereas you are showing the subsamples of the data and achieving a certain bit of accuracy, not an 100% accuracy or a maximum accuracy, but you are achieving a certain percent of accuracy and then combining. So it's not like you are achieving accuracy at the cost of your bias is increasing, where you are reducing, you're maintaining the bias and various trade-offs. In short, if people know what's bias and variance trade-off, then it is what we are achieving here. So I hope people know. So it's basically bias is nothing but you are introducing a certain error into the model when you're training, whereas variance is nothing but the error which you are getting after training the model from the test data. So when you trade off it, you want to get to an optimal point where the bias as well as variance is both are minimized. So this is what the bias variance trade-off is, and this is what we're trying to achieve it by generating the multiple subsamples of the data and training multiple decision trees and combining together. And in this way, we are overcoming the overfitting. I hope you have understood about this. So now let's go to the next mechanism, that is boosting. So in boosting, as we do is we train a sequential learner. That is, we train multiple weak learners, but one weak learner's output will be input to the another weak learner. And from the output of the as another weak learner will be input to the third weak learner. It goes on until and unless we achieve a required accuracy or required loss in error. So whatever we want to achieve, that's our objective. It second depends upon that. So this is what boosting is. Now the steps involved are basically train a classifier, that is say example C1, the best classifies the data with respect to accuracy, and then identify the regions where C1 produces error and add weights to them and train C2 classifier. So when I see here, so this is the difference what I'm trying to say from backing and boosting. In backing, simply you train a C1 and then move to C2 and then combine them. But here in C1, what you do is you train a classifier and then you identify the reasons. For example, the data points which are mislead classified. For example, there are two classes of 5 each, and you have classified 7 in one class and 2 in another class. The two misclassifications which are there, you will give a higher weightage to them, and you will pass the data to the second classifier. And the second classifier gives higher weightage to the misclassified data points and try to learn on that and then move further. So this is why, this is how the sequential learner, this is how the posting learner uh, works. and obviously repeat the about two steps to achieve the required accuracy or required minimum error. The biggest example is, or the whatever you say, that the common example or go-to example of boosting mechanism is AdaBoost. Now, what AdaBoost does is combines multiple weak learners, classifies that are slightly better than random guessing to create a strong learner. So, which is again a slightly better than random guessing. The classification problems are only supported here. The biggest catch is you cannot go for regression. You can go for only classification. You can do multi-classification, but you cannot go for solving regression problems using AdaBoost. You can do regression problems using XGBoost or XGBoost Lite or else GBM. So those again comes in our GBM methods, but so GBM methods will be discussing in detail further. But in AdaBoost, you'll be only be able to solving classification problems instead of regression problems. This is the drawback of AdaBoost. That I don't know how it works. It works by adjusting the weights of training examples based on their classification accuracy, so that the subsequent weak learners will focus more on misclassified example. Now, misclassification error is nothing. The probability of the ith example and the data set which you are using here. Okay, so to explain the terminology here, what I have given is HT is the hypothesis. Hypothesis is nothing but to put it in word, it's a model. It's a model which is giving you an output when you have trained it. So in mathematical terms, we call it hypothesis. So when we hypothesis, we give an input data. Xi is nothing but a data input or data record, and this is again coming from the dt is our data set. When it's not equals to yi is nothing but our actual what we say actual y values or the supposed to be predicted values, but here we it's not equals, then we'll simply calculate the probabilities and this will be our error. This is how the misclassification error rate for different misclassification weights of examples are calculated in a one single classifier, and then it gets propagated. I know it's very confusing for you guys, but let's deep down step by step for algorithm for AdaBoost. So for example, you have n sample size. So what's the first step is simply assign weights to each sample or each data record. Simply just divide the sample size by 1 and give a weight to it. The second step is nothing but training a model which gives the best accuracy. Train a logistic regression, for example, or train a decision tree, for example, which gives the best accuracy for the time being. Now again, after training the model, what we do is we calculate the weighted error of the weak learner. Again, I have explained the weighted error, how we are doing this. Where the weights are updated based on the accuracy of the weak learner. The accuracy of the weak learner is nothing the probability which we are getting from the model output. And obviously, if it's not equal to, we are matching it and then we are negating it, and this is the error. Now the again, this is the data points weights. Now here the weight of the classifier, the alpha t is called the weight of the classifier, because when we are saying that it's a sequential learning, we need to design the classifier learning also, right? So alpha t is nothing but it's given as mathematical equation, half of ln by 1 minus of error which we have calculated here. The calculated error is nothing but the classifier error which you have calculated. This is the weight of the big classifier. Now, to update the samples for the next time, now dt plus 1 is nothing but given a mathematical equation that is exponential negative to the alpha t. Alpha t is again we have calculated by this expression, and yi is the actual value of the data records, and ht is the probability which we are getting from the hypothesis or the model which we are getting, and zt is this whole divided by zt is nothing but it's a normalization factor. Normalization factor, you can say it's there are 10 data points or 10 sample size to the second classifier which we are going to, then simply divide by 10. So it will basically normalize it. So instead of varying too much, that is from -100 to 1000, so we are normalizing it to say 0 to 1 or -1 to 1 in between for the next learner. In short, we are scaling down the data points to speed up the learning. So this is what the normalization factor does. Now the step 6 is again repeat the step 2 to 5. I hope it's clear till now. If you have any doubts or if you're facing any problem here, okay, the Q&A session is there. We need to answer that. So I hope AdaBoost is clear. I will just give a quick recap. Initialize weights quickly to the data points which we have. Train a model, calculate the error of the model. Using that error, calculate the weight of the model for the classifier which we want to assign and then proceed further. Once you are calculating the weight of that classifier, use the weight to update the misclassified data points or the data points which you are passing to the next classifier by using the mathematical equation which has been given. It's nothing but exponential to the power weight of the classifier, the predicted actual values, and the vector values by not divided by normalization factor. If you want to skip, you can skip the normalization factor also, but obviously it will make your life worse only. The normalization factor will speed up your calculations and your model training, so it's required. So it's not mandatory, but you can get that. It's up to you. And again, repeat the complete process until and unless you achieve a certain accuracy or certain type of loss in error, minimization in error, whatever you want to achieve. So this is what AdaBoost does. I hope it's clear till now. Okay, the next method is basically gradient boosting mechanism. So now what gradient boosting does is it also a kind of sequential learner. It also combines multiple weak learners to get a strong learner. But the difference between the gradient boosting and AdaBoost is it tries to combine those weak learners by combining or passing the models in such a way the error is propagated from one model to another model and the error is minimized. In AdaBoost, what we are doing is basically we are updating the weights of each data points. That is, we are penalizing the misclassified one, and we are training the model again to get an accuracy so that the classification does to a certain extent. So we are basically passing the accuracy and improving the accuracy. Whereas in GBM, what we do is that we propagate the error from one classifier or one model to another model, and we try to reduce the error whatever we have got in past model and try to minimize the error in the coming models or coming up models in the sequential order. So this is how the gradient boosting mechanism differs from normal boosting mechanisms or AdaBoost what we do. The three things which we are required for gradient boosting mechanisms are loss function. Obviously, when we try to propagate the loss, you want to minimize the loss after training the model. So simply you can go for RMSE, that is root miscut error, or in case of classification, go for log loss or any other. And the other one is basically weak learner. So if you're using XGBoost gives you two mechanism, two models. That is one is decision tree and one is linear regression. I guess it gives logistic regression also. I have to check. So linear regression and decision tree both are used given by XGBoost, which is a type of GBM mechanism, which uses GBM mechanism. And the recent tech is basically cat boost. Cat boost is also a GBM mechanism. If you people are aware of cat boost, it's basically now taken into account for the Ensemble methods. Now people are directly going for cat boost instead of XG boost or XG light or any other methods. So hope GBM I have explained that people are clear about what it does. The algorithm involved are initially obviously predict the values for training example at a constant values. That is basically train a regression problem, use the mean value and calculate the error. That's what I'm saying, that root mean squared error, or in case of classification, just go for log odds or log probabilities. To train a weak learner, such as decision tree or a linear problem on the training data, where the target variable is the residual error of the predicted variables. So basically, you are propagating the error now, and now you are training a model on the weak learner. Now calculate the prediction of the weak learner and add it to the predicted values from the step 1. Now repeat the steps 2 to 3 until and unless you achieve a certain level of accuracy or minimize the error which you're propagating till now. Now combine the weak learners into strong learner where the prediction of each weak learner is weighted by its contribution to the final prediction. So the example of GBM is again XGM. It stands for extreme gradient boosting. It's a powerful and it's open loss and blah blah blah. You can read this slide. The biggest thing is why XGBoost came into play. Someone asked me questions like you want to optimize resource or you want to optimize time, everything. So XGBoost comes with three library features. One is parallel computation, that is, if you have 4 cores or 8 cores, it uses complete 8 cores, or it uses complete 4 cores, or you can use only 2 cores. You can specify to XGBoost how many cores it can use. Accordingly, it will train the number of decision trees and it will speed up your calculations and it will lessen down your computational cost. And now coming to scalability, you can scale it to any level by simply connecting to your cloud, or else if you have enough memory and you can use to encode and you can train to your cache memory, say 8 GB. Obviously 8 GB, if it's not big data, you can, or 16 GB, you can train say millions of records, at least 5 millions of records you can train on PC, until and unless you have 16 GB and 8 core PC. If not, then obviously you have to calculate what is the number of calculations your RAM can do, and is considered then big data, you have to go for cloud. But yes, XGBoost is scalable and obviously it gives fast and efficient because it's highly optimized one. And again, it gives regularization for the overfitting one using L1 and L2 regularization. The tree pruning, it's already there in random forest also, it's there in DataHour also. Tree pruning you can do. And missing values is an inbuilt support one, which is available in XGBoost, whereas in CatBoost also it is there. And cross validation is nothing but to get your accuracy of the model. It's just a type of overfitting, or somebody asked how it's kind of overfitting, because we are generating a lot of samples from the sample of data which you have. So it's kind of doing n-fold validation or cross-fold validation and then training models. In this way, we are overcoming the overfitting also. This is how XGBoost overcomes that. So I hope people are clear till now. So now let's dive into some practicals. Okay. Okay, so quickly I will give one example of the three things that is we have discussed. One of the bagging, that is random forest. One of boosting, that is AdaBoost. One of gradient boosting mechanisms, that is XGBoost. So we'll train on a sample set of data and try to visualize like how it's. So basically I'm importing the packages. So for XGBoost, you have to install XGBoost. So the simple installation mechanism is pip install XGBoost, pip3 install XGBoost. If you're using Python 2, then I think it will be your pip install XGBoost. And then for sklearn, I hope everybody has sklearn with them. From sklearn, just call the ensemble package, and from ensemble package you can call random forest classifier. And other thing is, if you want to call random forest regression, you can simply call random forest regression like this. Random forest regressor is also there. And another one is random forest embedding. Embedding should random trace embedding. It's for embedding, but it's not for training or something. It's called it is also the same ensemble method. It's used for embedding methods. But yep. This is for regressor, I guess. Random class forest regressor. So these are the packages for random forest, whereas for same ADA boost, this for ADA boost class boosting class. So what I have done is I will just restart the kernel. I don't know if it's killed or not. So hope everybody is comfortable with Python and Jupyter notebooks. So I have imported the packages, so these things are not required. But simply I am reading the data. So these are the data which I got, a sample set of data. If you want to check the shape of it. So it has 768 records and 9 features in it. So I'm considering the last features. Okay, I have just simply give the data set. So the eighth column is nothing but our target variable. So I have just split it into X and Y. This is my head and this is Y. I simply calculate for the value counts. It's basically imbalanced data. Zeros are 500 and 1 is 268. It's an imbalanced data. But again, kind of it's because we are training an ensemble method. We will be taking care of that also. Now I simply have just summarized my training data set, what are the mean, standard deviation, mean, etc. It's nothing but 0, 1, 2, 3, 4 are nothing. There are different kind of features like the parameters for the diabetes. So since I have picked up from internet that this particular data set, so I'm not sure exactly which particular column has which attributes, but to give an overview, these are something like sugar levels being impacted by your cholesterol, your heart rate, or else your daily walking methods. These are the parameters which are there, and this is one of the people's basically the target values. One means have diabetes and 0 means don't have diabetes. This is what the data at, to summarize or quickly recap it. So simply what I'm doing is I'm splitting up the data here and I'm using a test. Okay, so we haven't played it. So I'm simply using, instead of 30%, let's go for 20%. Okay, we have split the train RD start into X train, X test, and Y train and Y test. Now here I have defined the three models. One is the first one is the random forest classifier, and second one is Adabus classifier, and third one is basically XGB classifier. So I'm calling each models and making prediction, and we are training the data, fitting it, and making predictions. Once I'm predicting it, I'm calculating the accuracy using the y-test and predictions. So this is basically on test. It's not on the trend. So what I am calculating here is basically test accuracy, not the training accuracy. So let's do it. Okay, so for this particular method, the bagging method, that is the random forest, or you can say bootstrapping classifier, the random forest classifier, gives 81.17 accuracy. Whereas an AdaBoost gives, that is boosting classifier, gives 75.32% accuracy. And whereas GBM classifier, that is XGB classifier, gives 74.03% accuracy. Again, to quote here, this is just to give an example like how you can call the different classifier and how you can fit, how you can make predictions instead of writing the entire classifier on your. But again, different classifier and different parameters on it. So to call it, I'm calling it random forest. You can see different parameters in it. These are like n estimators, that is n-fold, how many. By default it is set to 100. You can go to 3. It will give you 3 different trees, decision trees, train 3 decision trees, and then combine. And then your criteria is Gini index, or else you can go for simple information theory, whatever you want. And the max depth, that is the depth of the tree. What is the max depth here? It is none. It goes on. And the minimum number of sample spread is 2. So you can go for n number of splits, a number of sample leaves are one. You can go for n number of leads. It's up to you. And simply for max features, XQRT, bootstrapping, and jobs, random state. So there are different parameters that random classifier has. And if you want to go in detail, so I have showed in your Jupyter notebook. You can go for the documentation also. It's simple. Go for random forest environment methods. Scalar. So here's a simple averaging methods, backing methods, and different type of random methods. Forest of random one. You can simply go here, ensemble random forest classifier. You have different parameters explained here. That's future importance, everything. You can go through this documentation, and you will get a better understanding what different parameters are there and how can I use. So they have given us few examples of using different parameters also, like n estimators they are using 10, and maximum tests they are using 9. So you can just experiment with it, so you will get a quick hands on it, weaker and study on it. And simply for CMG's ADA boost also they are different. Okay, this is not the one. Okay, so this is the one. So simply for ADA boost also you have different parameters. So here the estimator, you have to define what's the estimator and the number of estimator, what's the learning rate. Learning rate is basically nothing but the rate of minimizing the error loss function, which we can say. And the algorithm is SAMMER. Okay. So those who have already worked on AdaBoost and have already worked on basically ensemble methods might know this particular SAMMER and SAMMRE. So here I need to add one thing. This is nothing but the types of algorithms. One is SAMMER and one is SAMME. These are the two type of algorithm which AdaBoost gives. The first one is real. The second one is discrete. What is real means? Real goes and solves with probabilities. So since we have already defined that AdaBoost only solves for classification problems, we cannot solve regression problems with AdaBoost algorithm. So when we are solving classification problems, the outputs and the propagating weights, which we have discussed, can be done in two ways: using the real values, that is the probabilities of the classes, or else converting into the class that is 1 0 or 1 2 3 4, and then using this. The SAMMRE uses the probabilities at the real values. This is the algorithm. And SAMME is the discrete values which the AdaBoost use. This is the difference in AdaBoost classifier. So hope I'm clear here. So if somebody is interested, you can simply search for SAMME paper. It's a complete paper you will get here. This is the research paper. Those who are interested in research, they can completely read on this one. It's a complete example, or you can show simply go for okay, it's just okay. Scikit also, sklearn also gives the description. It also does that uses a priority estimates to update the activity model, whereas SM use the classifications only. So it says the same. So whatever you want, if you want to deep dive further, you can read on it. It's a complete research paper I have. I know, like there is a research paper. I'm not recalling it right now. Uh, so whatever, okay, it's there. So 2009 paper mentioned does not include SMNR. Okay, so you can go through it. Okay. Apart from that, what XGBoost has, XGBoost is not a part of sklearn. It's a completely different package. Now what XGBoost classifier does is objective function. Objective function is nothing but you keyword different types of data set and different basically model which you want to train. That is binary logistics. Here it's by default defined binary logistics, but you can go for basically a decision tree also, random forest also. And then basically label encoder is optional and other methods. Okay. Here are the different types of parameters which you can, again the same thing, and estimators, maximum depth, maximum leaves, everything. So you can go through it. So hope I am clear till now. I'll just quickly shift. Okay, there are 9 questions. I will take it. Shall I take it right now, or shall I continue with the practicals?
So before we proceed to answer the questions, I would like to request the attendees to please fill the poll about feedback, as it will help us to conduct more such sessions. After that, we can move on to the Q&A part.
Okay. So shall I complete the rest practical that Python code also, or shall I take up the question and answer?
Because it looks like there is time constraint. We are already 14 minutes past the expected time. So I'll request you to take the Q&A and let's see how many learners are there. Then we will be able to move forward.
Okay, okay.
Thank you.
There is a database regressor as for regression problem, right? No, I have to check it because I haven't used it till now. So let me check it. If it's there, then if it's there. Oops, sorry. This is Ensemble methods. Yes, it's there. It's there. And the second question is explain the algorithm with some sample data. Which algorithm you want to do right now? If you're talking about adabos, okay, I will do it. Why do we use subset of features in random forest? Okay, so subset of features depends upon your selection. So it depends upon how you are generating the subsample or bootstrapping it. So when you say bootstrapping is nothing but generating a subsamples of data from the sample of data which you have. Now, when you're subsampling it, the subsampling can be done in any ways, right? If you go for sampling techniques, there are many sampling techniques. One is random sampling is there, one is collaborative sampling is there, one is filtering sampling is there, one is basically, okay, I will just show that one also. Sampling techniques in Python. Okay, so this depends upon the type of sampling which you're using. So when random forest is there, basically you are mentioning the different types of sample size. But if you're not sampling on the features, we can sampling on the different features also. It's the number of estimators you're saying is nothing but the number of features you have to split on the basis of that. So this is the sampling techniques which are there. You can use different type of sampling, that is probability sampling. So you can go through different types of sampling. It's nothing but the type of sampling which you're using. That's why the subset are created, the subset of features and random forests are created. Hope Chirag, I have answered your question. So random forest also works on the probability approach to decision trees. Yes. Or it has some other set of rules apart from the combination of it. No, it works on the probability of approach of decision trees. So basically, it's nothing but you can take say 10 decision trees. 10 decision trees are working or training parallelly, gets trained parallelly. But the decision tree working, again, it's just by splits, and then obviously taking the probabilities. And once it's there, you are basically combining those together and then calculating the loss, that is the mean loss or the aggregated loss, whatever loss you're calculating it. So Gulzar, hope I have answered your question. I feel even random forest overfits. Yeah, that's what I'm saying. It overfits. It's there, not completely taken care of, but the overfits is taken care of in cat boost, or else you can go for XC boost. It depends upon the type of training area again. The pruning is one of the methods where you can improve the overfitting. You can also improve the overfitting by describing the depth size, and you can also improve the overfitting by describing the gradient method which you are choosing. So it depends upon different things. For example, cat boost gives the options for us to tweak on different parameters, and you can come overfitting. But random forest, yes, it still has overfittings. I have said in my presentation also. Yeah. And what about out of bag sampling in bagging ensemble? Does the model automatically separate out the samples from each learner? And does that mean the training data per learner is reduced to the extent? Okay, in tagging engine, does the model automatically separate out the sample model automatically separate out the sample from each learner? Okay, okay, I got it. So you are saying that sampling with replacement or without replacement, so it doesn't take define like that. So when you are saying that random sampling in case of random forest, you have to mention with replace or with a, but if you by default, if you're not mentioning it, it doesn't separate it out. For example, if you have taken 10 records here and 10 records in the next sample, there is a probability that sample the number of the data points will get repaired. But again, there is a option for you. There's a parameter. You can mention it. You can use different subsamples. It depends upon you. Natraj Lagudi. So it's a parameter simply. So with replacement, without replacement, it's up to you. You can tweak it and you can sample it. And does the mean that the trained data per learner is reduced to the extent? You can say overallly, since you are training different subsamples and you're combining it, so you are actually reducing the difference in mean prediction means and the actual means which you are having it. So at an overview level, you are reducing the mean only. Yes. That was why or how ensemble methods reduce variance. So obviously you are creating different subsamples of data and you're showing subsamples includes also different features and you're not basically taking on different one particular data one and it goes on different feature dimension wise, like if you're defining in two dimension wise, one is the depth of the data and one is the width of the data. You are both ways you're sampling it and you are training the models, different models, and you're aggregating it. So in that way, the variance in one models will be taken care of whatever variance you're getting in different method. So it's propagated there and the rest variance is taken care of the next model. So in that way, we are making sure that it's reduced. I'm not saying that it will go to zero. I'm not saying that it will completely vanish, but we are trying to reducing it and we achieve certain level of accuracy in reducing the variance. Murli, I hope I have answered your question. How does it reduce overfitting? I hope we have taken this question. How do you decide which, okay, this we have answered before already. Are the features okay? Thanks, Apart. Please, can you share with us any source of materials about enzymes, include PPT and codes? Okay, how to share this? I can share the code and PPT, no issues. But how to share? I don't know. How do you use subset of features in random forest? We have answered this. Are the features in random forest selected randomly? In that case, what if it ends up not selecting the features which is slightly correlated with the output? Not selecting the features which are highly correlated with the output. So that's what I'm saying. When you're selecting the features randomly, you are feeding it to only one decision tree. You're not ignoring the complete feature. You are training the with the, say there are 10 features. You're training with the 10 features. But when you are training a particular decision tree, you are reducing it. But the accepted feature that is say one of the feature which is highly correlated with the output, that is the better that is the target variable, and it is in different tree but not in this particular decision tree. Say there are two decision trees. One decision tree has say 9 features and another decision tree has say 8 features, and the highly correlated feature which is there is present in the model on the decision tree, which is 8 features, will give an higher accuracy and this will give a lower accuracy. And when we are combining it, we are learning it that this particular feature is being given more weightage. This basically we are trying different trees and combining. We are not ignoring any feature. Hope I have understood it. Hello. I think as it we have answered all the questions.
Perfect.
Shiva.
Thank you, Vikas. Thank you so much.
So if people want still there, so I can go through cat boost coding, or else if you want to drop, so we can end it. It's up to you.
So, Vikas, basically, we have another session lined up in
Okay.
minutes. So, I'll request you, we can connect on mail, and if any of the learners wants any other resources, you can provide us over there. Also, I have shared your LinkedIn profile to everybody. They can also directly reach out to you as well. Okay, thank you, Vikas. And on behalf of Analytics Vidya, thank you so much for your time and for delivering such a wonderful.
Sure.
I'm
Okay.
sure our audience found it insightful, and hopefully we can conduct more such sessions with you in the future.
Yeah, sure. It's a pleasure from my end and also. So there was a little bit of glitch at the beginning, but yeah, it's
Yeah,
fine.
yeah, was resolved. Thank you. Thank you so much, Vikas.
Thank you guys. Thank you everyone. Thank you for attending.
And I hope everyone has filled up the feedback poll. If not, I request you to please do, as your feedback is valuable and it helps us to conduct more such knowledgeable sessions. And the recording of the session will be available within 2 days on our YouTube channel. The link I'll be providing in the chat section. Also, we are having another session from 3 p.m. The link I'll be providing in the chat section. So hurry up and register for that. See you in upcoming data sessions as well. Till then, bye-bye and keep learning, guys.
Thank you guys. Thank you. Take care. Have a great day.